8 o'clock in the morning, March 10th, 2019. Bole International Airport, Addis Ababa, Ethiopia. At one of the passenger terminal gates, Ethiopian Airlines Flight 302 is finishing its final preparations for departure. This is a scheduled international flight from Addis Ababa to Nairobi, the capital of Kenya, landing at Jomo Kenyatta Airport. It lasts just over an hour. The aircraft getting ready for takeoff is a Boeing 737 MAX 8. It was built in 2018 and delivered to Ethiopian Airlines on November 15, 2018. At the time of the accident, its total flight time was 1,330 hours over 382 flight cycles. The cabin layout is multi-class with 160 passenger seats. Formally speaking, it was nearly a brand new aircraft, less than 4 months in service. One owner, the leasing company, Ethiopian Leasing, operated by Ethiopian Airlines Group. In the weeks leading up to the flight, the jet underwent scheduled maintenance. In early February 2019, it had a routine A-check inspection. This is a general visual inspection and a standard set of maintenance tasks. In the technical log were isolated issues from previous flights, sporadic fluctuations in airspeed and altitude readings, occasional complaints about autopilot performance. According to the report, corrective actions were taken in all cases, and those faults did not recur. In the preliminary reports section on technical condition, no outstanding faults or unusual maintenance were noted immediately before Flight 302's departure. A key feature of this Boeing 737 MAX variant is the MCAS system. It uses input from a single angle of attack sensor and makes small pitch adjustments via the stabilizer if it believes the aircraft is approaching too high an angle of attack. MCAS operates automatically with no separate indication on the panel, and pilots cannot control it directly. MCAS was introduced because the 737 MAX got new CFM International LEAP 1B engines. These engines are about 14 to 15% more fuel efficient than the previous generation, but they have a larger fan diameter. To maintain ground clearance, the engines were mounted higher and slightly farther forward compared to the previous 737 model. This change affected the plane's aerodynamics. In certain configurations, it created a stronger nose-up pitching moment. To keep the handling characteristics familiar and make the transition from older 737s to the new MAX easier for pilots, engineers added an automatic system that would make minor pitch corrections when the nose rose too high. The idea was to make the 737 MAX fly as similarly as possible to earlier versions, reducing retraining time for crews, a key competitive advantage over Airbus. Flight route: Addis Ababa, Ethiopia to Nairobi, Kenya. It's a short international hop between the capitals of two neighboring countries. According to the commercial schedule, such flights usually last just over an hour. There are 157 people on board preparing for departure. The captain, first officer, 5 flight attendants, 159 passengers from 36 countries, and 1 IFSO, an in-flight security officer, an air marshal responsible for on-board security. But one passenger didn't show up for this flight. He was a Greek citizen who missed boarding by about 2 minutes and didn't make it onto the plane. The captain was Yared Getachev. He was only 29, but his flying experience was already substantial. 8,122 total flight hours, including 1,417 hours on the Boeing 737 and 103 hours on the Boeing 737 MAX specifically. His last simulator check took place in the fall of 2018. At Ethiopian Airlines, he was seen as one of the promising young captains, confident, calm, and well-trained. The first officer was Ahmed Noor Mohammed. He was 25 years old. By the time of this flight, his total flight time was 361 hours, including 207 hours on the Boeing 737 and 56 hours on the newest Boeing 737 MAX variant. Ahmed Noor had recently completed his Boeing 737 training and was already flying regular line flights with Ethiopian Airlines crews. Weather conditions at the airport were good. Visibility was about 6 miles. There were a few clouds and a light northeast wind. The runway was dry. The air temperature was around 55 degrees Fahrenheit. At 0827, the controller clears Flight 302 to taxi to runway 07 right. The plane begins taxiing from the gate. Nothing unusual happens at this stage. A normal, busy morning scene at a major aviation hub where dozens of planes are getting ready for the first flights of the day. The plane keeps moving and arrives at the holding point for runway 07 right. 8:38. The crew sets flaps to 5 degrees, the standard takeoff configuration for a Boeing 737. The captain advances the thrust levers to take off power. Both CFM International engines smoothly spool up to maximum thrust. The Ethiopian Airlines jet begins its takeoff roll. Speed rapidly increases. Very quickly, the jet reaches V1 speed. That's about 175 miles per hour. At this point, you can't reject the takeoff anymore. Speed approaches VR, rotation speed. The captain smoothly pulls back on the yoke. The nose lifts up, and a moment later, the jet leaves the runway. The Boeing 737 MAX begins climbing over Addis Ababa. But almost immediately after takeoff, one of the angle of attack sensors, which measures the angle of the oncoming air, suddenly starts showing wildly inflated readings. At that same moment, the captain's yoke begins to shake, indicating a stall condition, even though the plane continues climbing and is in normal flight. Altitude is climbing, 200 feet, then 330, 400 feet. The captain keeps climbing and, once at a safe altitude, tries to engage the autopilot. That's a standard step after takeoff. But the system won't engage. A short rejection tone sounds in the cockpit, and the autopilot does not activate. A couple of seconds later, the captain tries again. Same result. The autopilot rejects the command again and stays off. The plane continues climbing manually. The Boeing is going up to around 1,000 feet. By this point, parameters have stabilized, and the captain makes another attempt to turn on the autopilot. This time, the system accepts. The autopilot engages, and the aircraft switches to automatic heading control. However, it doesn't last long at all. Almost immediately, the plane starts to wander slightly and roll, little jerks left and right, as if the autopilot is trying to hold the climb path, but doing it unevenly. After a few seconds, the autopilot disconnects. Control reverts fully to the pilots. After the autopilot disengages, the crew continues flying manually. A few seconds later, the first serious deviation occurs. The stabilizer begins subtly moving nose down, and the aircraft's nose drops slightly. The captain feels it immediately because of the increasing force needed on the yoke. To maintain the climb path, he pulls back on the yoke, compensating for the decrease in pitch. This stabilizer movement is not a pilot command. It happens suddenly, like the action of an automatic system that mistakenly thinks the flight is approaching a critical angle of attack. For several seconds, the crew holds the plane manually, countering the nose drop. The sensor that gave false readings keeps affecting the automation, and the pilots have to apply more and more force to the yoke. The jet is still climbing, but holding the correct pitch becomes harder and harder. Despite the first automatic nose-down attempt, the crew holds the plane where it should be, countering with manual force and elevator deflection. For now, the aircraft remains level in pitch. But only a few seconds pass, and the stabilizer starts moving down again, this time noticeably faster and more aggressively. The nose drops, and the yoke force sharply increases. The captain has to pull back on the yoke almost to the limit to keep the jet climbing. At this moment, the airspeed starts increasing rapidly. The plane accelerates significantly faster than normal for this phase of flight. The higher the speed, the greater the aerodynamic forces, and the harder it becomes for the pilots to hold the stabilizer manually. The 737 MAX is still climbing, but the climb angle becomes less and less stable. MCAS keeps trying to push the nose down, while the crew keeps trying to hold it up, pulling harder and harder. The yoke vibrates continues. To reduce the growing yoke force, the captain presses the electric trim switch, making a brief adjustment. The stabilizer moves up slightly, and for an instant, the controls feel lighter. But just a few seconds later, another automatic pitch-down command comes in. The stabilizer goes down again. The yoke force returns, now even more pronounced. The crew understands the automatic system is still interfering with the controls. The captain makes another brief attempt to trim the stabilizer, but the automatic input cancels it out again. The pilots decide to cut off electric stabilizer control. On the center panel, they move both stabilizer switches to cut out, completely disabling the electric trim motor. The automatic commands stop. The stabilizer no longer moves. It stays where it was at the moment of cutout. Now all pitch control is done solely via the yoke, with no trim assistance. But the plane has already accelerated to a high speed, and the aerodynamic forces on the stabilizer are large. Moving the yoke is incredibly heavy. For a few seconds, the Boeing keeps climbing, but the climb angle gets shallower and shallower. Then the altitude begins to slowly sink. The crew pulls the yoke with all their strength, and the plane starts climbing again, but now at the very limit of manual control at that speed. Holding the correct pitch is now practically impossible. The jet is flying at high speed, the stabilizer is stuck in an unfavorable position, and the captain is pulling the yoke with maximum effort. Realizing that holding the plane manually at this speed is nearly impossible, the crew decides to turn the electric stabilizer control back on, even though they had turned it off just seconds earlier. The stabilizer switches are moved back to the on position. The captain tries again to trim the aircraft, pressing the trim switch on the yoke, but immediately afterward the automation kicks back in. The stabilizer moves even farther nose down, more aggressively than before. The nose starts dropping, and the speed increases even faster. The yoke force becomes critical. The captain pulls it all the way back, but that is no longer enough to keep climbing. The Boeing begins a pronounced descent. At high speeds, the aerodynamic loads become enormous, and the captain applies incredible force, pulling the yoke fully back. This is the maximum possible manual force. But even with that, lift can no longer overcome the effect of the stabilizer, which is in a nose-down position. The 737 MAX rapidly loses altitude. The crew keeps holding the aircraft, doing everything possible to raise the pitch. The yoke remains fully pulled back. Meanwhile, the speed has gone far beyond normal flight parameters and reaches nearly 500 miles per hour. At such speeds, pitch control becomes ineffective. The aircraft barely responds to inputs. The Boeing is descending rapidly, now almost unresponsive to the crew's actions. The altitude margin disappears in a matter of seconds. At 500 miles per hour and a 40-degree angle, the Boeing slams into the ground. All 157 people on board are killed. The plane crashed into an agricultural field near the village of Ejere and was completely destroyed. The impact leaves a crater about 33 feet deep and around 130 feet wide. Most of the wreckage was buried in the ground, with small fragments scattered over an area of about 15 acres. In such a crash, survivability is zero. On the day of the accident, Ethiopia's Ministry of Transport and the Aircraft Accident Investigation Bureau were notified that radio and radar contact had been lost with Flight 302. After the crash was confirmed, Ethiopian authorities launched an investigation in accordance with ICAO Annex 13. An investigation committee is formed with the following participants: Ethiopian Airlines, technical advisors; the NTSB, because the aircraft was designed and built in the U.S., the BEA, for their work in reading the recorders, and EAASA as a technical advisor. On March 11, 2019, the digital flight data recorder and cockpit voice recorder were recovered from the crash crater. The recorder housings and memory modules were sent to the BEA's laboratory in Le Bourget, France. There, under the supervision of the Ethiopian Commission and with NTSB representatives present, the data was read out. The Commission's official findings contained 88 points, but we'll list the most important ones. The root cause was a faulty left angle of attack sensor. It transmitted a false reading immediately after takeoff. These false readings activated the MCAS system. It mistakenly concluded the aircraft was stalling and began automatically issuing nose-down commands. MCAS repeatedly moved the stabilizer to a nose-down position. The crew lost the ability to control the aircraft's pitch, after which the plane entered a steep descent and hit the ground. Overall conclusion: the accident was caused by false angle of attack sensor data that triggered repeated automatic nose-down commands from the MCAS system, which moved the stabilizer into a position from which the crew could not maintain normal flight. This disaster served as a reminder that even the most advanced aircraft remain vulnerable if key systems are not properly tested and validated. New technologies can make flying safer, but any underestimated change to flight control automation, any insufficiently tested or poorly designed innovation, can lead to consequences that no crew can prevent once airborne.